Okay, in this presentation, I want to go through definitions, equations, units of key parameters covered in biomechanics in a biomechanics focused class. These terms are important to just know the definition of, and equations where appropriate, and units where appropriate as well. And that allows us to start having conversations using these terms when at least we agree on definitions. So what I'm going to do in this presentation is I'm simply going to go through quickly the definitions, equations, and units, again, where appropriate. I'm not going to go into detail explaining each parameter. I have other videos for that, and you should make sure you understand the parameters, but we have to often start with a definition and then work off of that. So this is going to be fast. I'm actually not going to write anything, but I'll go through the parameters quickly, and you should be able to listen along and jump, beat me to the definitions, equations, and units. All right, let's start with displacement, a straight line distance between 2 points. The symbol we use is S in this class, can be any other symbol in other classes, but delta S equals final position minus initial position, and the units are any units of length: meters, yards, centimeters, kilometers, miles, any units. Displacement is a vector. Remember, vectors are represented by magnitude and direction. So we need two things to describe a vector. Distance is a scalar. It's represented by magnitude only. And it's the total change in position an object goes through. So if we follow the path of an object, we would measure the length of that path, and that would be distance. There's no equation for distance because we're actually measuring the path that the object follows. The units are any units of length: meters, yards, centimeters, kilometers, miles, any units of length. It is a scalar. It's represented by magnitude only. Velocity is rate of change of displacement, how fast position is changing. The equation is V equals delta S over delta T, final position minus initial position, divided by the change in time. Units are any units of length over any units of time. So meters per second, meters per minute, miles per hour, kilometers per hour, any units of length over any units of time. Velocity is a vector, and it's represented by magnitude and direction. Speed is a scalar. It's represented by magnitude only, and it's how fast distance is changing. So this is the total change in position divided by delta t. There's not an equation other than distance over time. Units are units of length over units of time. So meters per second, miles per hour, kilometers per, any of those. Velocity and speed are similar, but velocity is a vector and speed is a scalar. If you're in a physics class, your prof may say the speed is the magnitude of the velocity vector, which is fine, that especially when the delta t that we're looking at is really small. Same thing with displacement and distance. Your prof may be telling you that the magnitude of the displacement vector is distance. It's fine as long as the delta t we're looking at is really small. When we start getting at bigger delta t's, distance and displacement can be different parameters or different magnitudes. Acceleration is time rate of change of velocity. A equals delta v over delta t. Any units of velocity over any units of time. Meters per second, which translates to meters per second squared. Miles per hour per second, perfectly fine acceleration set of units. Any units of velocity over any units of time. It is a vector. It's represented by magnitude and direction. The key with the acceleration vector direction is that does not tell you direction of movement. The direction of the velocity vector will. The direction of the acceleration vector does not tell you which way the object's moving. Absolute angle and segment angle are the same exact thing. They represent the angle of an anatomical segment relative to a fixed line in space. So a segment would be the arm, the forearm, trunk, leg, thigh. Those are segments. Foot. We need to have we represent the angular position of that segment relative to a line that does not move. For example, a horizontal line, a vertical line, something like that. The trick with absolute and angular absolute and segment angular positions, is defining where that relative line is. So we would have to use language like a right horizontal projected at the distal end of the segment. All that's doing is telling us the fixed line. Then we identify the angular position of the segment relative to that fixed line, which does not rotate. Relative angles are the same as joint angles. They are the angle between two anatomical segments, both having the ability to move or to rotate. They don't have to rotate, but they both can rotate. Angular displacement and angular distance I don't have on here, but we would start taking those angular positions and start quantifying change in angular position. Angular distance is the total change in rotation of an object. So if we start doing multiple revolutions of an object, we would start accumulating angular distance. Angular distance is simply the final angular position minus the initial angular position, and that's a vector. We use the symbol theta to represent both of those. Angular displacement is the vector, angular distance is the scalar. Units are units of radians or degrees. We could also use fractions of a revolution as well. Angular velocity is time rate of change of angular displacement. So it's delta theta over delta t. And the units are the units are units of either radians, degrees, or revolutions per time. So any units of angular position over any units of time. So radians per second, degrees per minute, revolutions per minute, any of those are fine units for angular velocity. It is a vector. It's represented by magnitude and direction. And the direction will tell us the direction of rotation. Angular speed is the rate of change of angular distance. And again, same set of units, either radians, degrees, or revolutions over time. We would start using the angular speed if we start looking at a big delta t, like looking at how the average speed during a 2.5 somersault revolution. The 2.5 somersault would represent the angular distance. The delta t that happens in would then allow us to calculate angular speed. Angular distance, or just going to be angular displacement, is simply the final minus initial position. Angular acceleration is the time rate of change of angular velocity. It's how fast angular velocity is changing. It's a vector. It's represented by magnitude and direction. The units are any units of angular velocity over any units of time. So degrees per second, or degrees per second squared. Revolutions per minute per second, any units of angular velocity over any units of time. It is a vector. It has magnitude and direction, and the direction of angular acceleration does not tell us the direction of rotation. Okay, then we get into kinetics. Force is the tendency of a push or a pull that tends to cause movement. The equation we start off with is F equals ma, and the units being newtons. We'll get to some other forces that we have down at the bottom of this list, and they have different equations, but they all have the same set of units. Units of force are newtons. Inertia is the resistance to change motion. So if an object has lots of inertia, it has lots of resistance to change the motion. Motion can be thought of as velocity. So hard to get it. If an object has a lot of inertia, then it would be hard to get moving. And if it is moving, it'd be hard to stop it from moving. No equation for inertia, but it's represented by the mass of an object, and the units for inertia are kilograms. Impulse is the how long a force is applied, and it's represented by the equation F delta T, so force times how long that force is being applied, and the units are Newton seconds. Momentum is the quantity of motion, and it's represented by the equation mass of the object times the velocity of the object, and has units of kilogram meters per second. Torque is the tendency of a force to cause rotation. We start off with the equation T equals FD perpendicular. F is the magnitude of force. D perpendicular is the moment arm. And torque is a vector, is magnitude and direction. and the units are Newton meters. Moment is the exact same thing as torque. Moment of inertia is an object's resistance to change rotation, and it's represented by the equation I equals sum of mr squared, where m is mass particles and r is how far that mass particle is from the axis of rotation, squared. So sum mr squared. Units of moment of inertia are kilogram meters squared. Angular momentum is the quantity of angular motion, and it's represented by the equation moment of inertia times angular velocity. So moment of inertia times omega. And the units are kilogram meter squared per second. Work is the application of a force over distance, and so the equation is FD. It also represents the energy transferred to an object from one object to another. The units for work are units of joules. Energy is the capacity to do work, and there's all different forms of energy: light, heat, sound, mechanical. All these have different forms of equations, different way to represent them, chemical, but they all have the units of joules. Potential and kinetic energy are forms of mechanical energy. Potential energy is the capacity to do work based upon maybe position, and then we use the equation mgh, or maybe it's based upon how much a spring is stretched or compressed, 1/2 kx squared. Potential energy still has the units of joules, and it's the potential to do work based upon something. Kinetic energy is the capacity to do work based upon motion, and the equation that we start off with in the linear world is 1/2 kv squared. We also have the angular kinetic energy, 1/2 k omega squared. All forms of energy have the units of joules. Power is how fast work is being done, so rate of work done. Another way to think about this is how fast energy is transformed from one state to another. I always use the light bulb. We take electrical energy and transform it to a light energy. How fast that does is the rating of the light bulb. So a 30-watt light bulb is not as bright as a 60-watt light bulb, where the wattage tells us how fast that energy is being transformed from one state to another. The equation for energy, though, in the mechanical world is work over time, and we can derive that a little further, and we can get work is also the product of a magnitude of a force and how fast that force is being applied. Sorry, product of force and how fast that force is being applied. The units for power are watts. So then we get into some other forces that we want to talk about. Drag force is the force applied to an object that's moving through a fluid. And the equation we work with is 1/2 rho CdA V squared, where rho represents the density of the fluid. CD is the coefficient of drag, which represents how well or how easy a fluid moves over an object. That's based upon how smooth the object is, as well as the shape of the object. A is the frontal area being moved through the fluid, and V is the how fast the fluid is moving over the object, and we square that V. So 1/2 rho CdA V squared. It's still a force, still has units of newtons. Air resistance force is the same as hydrodynamic drag force, so moving through the water and getting a resistance of the water pushing on the object. Remember, drag forces can be resisting forces, but they can also be propelling forces. Buoyancy force is the upward force a fluid exerts on an object. That equation is rho times the density of the fluid times the acceleration due to the force of gravity times the volume of water displaced. And we actually make that a negative number. But if we use it negative for acceleration due to the force of gravity, that's a positive force, meaning it's an upward directed force placed on the object. In the unit for buoyancy force, it's a force, so it still has units of newtons. Friction force is the force exerted on an object due to movement of an object over another surface or another object. And the equation we use is mu times the normal force, or the force that's perpendicular to the surface that being moved on. It's a force, so the units of friction force are units of newtons. Newton's laws of motion, you should know these. The law of uniform motion, an object will stay with its state of motion unless a force causes that motion to change. That's an observation. Second law is when a force acts on an object, it will cause the object to accelerate. So force equals ma, tells us how an object actually moves. And the third law is really Newton's law. The other two existed prior to Newton. For every force acting on an object, there's an equal and opposite force created by the object, or vice versa. Every force created by an object, there's an equal and opposite force acting on the object. The key with using these laws is use them together, and Newton's second law is we add up all the forces acting on the object, and that equals the product of mass of the object, the inertia, times the acceleration of the center of mass of the object. Equations of constant acceleration I put on here. Those are just good to have in your back pocket. They do come in handy, but VF squared equals VI squared plus 2A delta S is one of them. The other one that I like to just commit to memory is final position is equal to initial position plus the product of the initial velocity times time plus 1/2 AT squared. That equation is nothing more than a second order polynomial, and that actually describes that parabolic motion that a projectile goes through when it's flying through the air without any other forces other than gravity acting on it. Last term I have on here is pressure, and that is just force applied per unit area. It's force over area. In this case, the units for pressure, we'd start with pascals. There are some other units for pressure, millimeters of mercury and what have you. There's different ways to represent it. But in the mechanical world, we would use Pascal, and that would represent the force per unit area. Okay, so I did that quickly, and you should be able to listen to this video and go right along with me on the definitions, equations, and units. If you don't understand some of these parameters, that's where we go back to or go forward to some of the videos that we go through in this class or other classes that I've done on biomechanics. All right, I hope this is helpful, but this is the position I want to get you in as you go into a final exam. Know your terms, know the definitions, know the equations where appropriate, and know the units where appropriate. Okay, thanks everybody.